Welcome to our third podcast of Unit 3. We're at the top of page 12. Still talking about electrons, but going to talk about a little bit how electrons move within that atom and what happens when these electrons are moving. So first, we're going to start talking about EM, electromagnetic radiation, the EM spectrum, or light. When we see light, we typically think of just visible light. There's actually more to the EM spectrum, more to light, than just the visible spectrum. So when we say the EM is just some form of energy that exhibits wave-like properties as it travels through space. Look at your examples. There's visible light, which typically, like I said, when you think of light, X-rays, UV, ultraviolet, infrared, microwaves, radio waves are all types of the EM spectrum. Okay, so I like this picture. Look at the wavelengths. And at the top, you have some things you could write in. What do I know about my wavelengths? You have long wavelengths on this end. See, this is what it's talking about. This is what a wave is. From the top to a top, that's one wavelength. See how long this is? Going to very short wavelengths over here. So frequency, okay, also down at the bottom, frequency is how often does that wave pass a specific point. So if you have long wavelengths, that also means then you have low frequency at this end. And look at these. They're very short, so that means they're hitting a lot of time. So these have a very high frequency. And so look at if it has a low frequency, low energy, high frequency, high energy. I don't have to write all of these, but look at what I would know some references. Radio waves are very long, low energy. That's why you can walk all around you. Microwaves, then you have infrareds. Okay, visible. Draw something here to kind of the visible. This is what we're going to care more about. What do I care about this? Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Red, orange, yellow, green, blue. This is indigo, which is like a almost blue, purple, and then violet. The color spectrum. So Roy, red, is on the low frequency, long wavelength. Violet is on the high energy, high frequency. The way I think of it, violet is very close to UV. We know we can get burned and UV rays can have damage. So do I need to know this order? Yes, yes you do. Then we have our X-rays and our gamma rays that could have more harm because they're going to be at a higher energy. So there's a question there. Why will yellow light cause the ejection of electrons? What happens is called the photoelectric effect. And this is pretty much how your remote control looks. That if I shine a light, you could actually, if it has enough energy, it's going to cause some electrons to go out of that metal. But look at down here. Why does yellow light work but not red light? Because yellow light has a higher energy than the red light does. Okay, so what does this have to do? Why are we talking about this? Okay, let's relate it back to what we're seeing in the atom. So this was Niels Bohr. So remember talking, we had worked up to Rutherford, and Rutherford had nobody really knew where those electrons were. They just were in a cloud running around. So Niels Bohr started doing some experiments. Some background and some vocab you need to know. So ground state is the lowest energy state. Okay, this is whenever you write configurations, you're writing ground state configurations. It's normal. So 1s2, 2s2, 2p6, that's the ground state emission of neon. It's just the normal state of it. Excited state is when it has a higher than it's supposed to be. So if all of a sudden I see something at 1s2, 2s2, 2p5, and then you have a 4s1. Okay, that looks weird. So that's my hint to you. If something just looks weird, it's been excited. And so an electron, this electron has jumped up to a level that it doesn't belong in. Okay, so that's what it means, is when something is temporarily not at its normal state. So that happens if you add some energy is applied. This could be my process. Let's say I have a cattle prod. If anybody knows a cattle prod, it has electricity at the end. It's kind of like a stick that has electricity. And let's say somebody's sleeping in class. So I'll let you put your own names in it. And if I put a cattle prod to them, I bet they jump up. That's what this electron doing, is jumping up. Okay, that is when then you would say that they're probably pretty excited. They woke up pretty excited. But just like that person, electrons can't stay there. So what happens, look at energy then is released when they come back down, and you're going to see an emission usually in the form of colors. And I bet that person, if they actually after they had gotten woken up and jumped up, they probably emit some pretty colorful language as they're coming back down. Just like these electrons are going to do, emit some colors as they come back down. That's what we're interested in. This is how we justify and we talk about the flame test lab. So what had happened? We just thought, again, I was not there 200 years ago, but they had thought that if the electrons were everywhere, this is what they expected to see. They're going to see every color because those electrons could jump multiple and infinite difference of energies. Okay, what they actually saw then was a line emission. So look at the difference. Make sure you just know the difference. You could even write in the box, all this for a continuous spectrum, all colors. Look, there's no break. Emission spectrum, there's only a few. There's like a red here, then there's a yellow, maybe a few greens. You only see few lines. Okay, we will be looking at these in class. Problem is we don't know when. Mrs. Rowland's class will get it one day and we'll get it another day. We only have one machine that can do this, so we're just going to have to kind of share it. So either in the next couple days you will get to see some of these line emission spectrums. So this is what they did. He took hydrogen, okay, Niels Bohr, put it through a slit and then put it through a prism expecting to see all the colors. That didn't happen. He only saw some colors. So that was a big deal, a big deal. Because remember, a lot of these discoveries were made by seeing this evidence. So his evidence, he's looking at this, it's like, oh, okay, electrons cannot go everywhere in an atom. They can only go in certain set energy levels as you're going through it. So he identified these series, and they were identified actually by different people, listed by their names. Some of them, as you can see, were later when you had the pieces of equipment. These are the hydrogen, and we will look at the hydrogen emission spectrum, but found something unique. Every element had a unique spectrum as you looked at it. So Bohr came up with the Bohr model then. He said, okay, now you have these lines at the bottom of page 12. After those lines, you can fill it in. So Bohr said that each line that he saw was produced by the emission of photons. Okay, this is a little packet of energy. We're going to come back and talk about that energy, of certain energy, not protons. It's not a typo. It's a photon. And so look at what happens. You applied energy. This energy, so this is my energy right here. This is your energy coming in. The energy is my cattle prod. What did it do? It caused the electron to jump up. So let's say, to be equal, it caused this electron to jump up. It cannot be stable. So look at what happens. It comes back down to its normal level. This energy right here is emitted. So look at the difference in the vocab. This is energy absorbed. Energy absorbed causes the electron to jump up, not stable. This is the one you care about. It's when it's emitted. 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 That is when you see the light. And so this energy difference transfers into a different frequency, which turns into a different wavelength, which means you see different colors. But look at, there's only this energy difference, so it means there's only this frequency. There's only this energy difference, which means there's only this frequency. Nothing in the middle. It's kind of like an elevator on the lines, elevator on a building. Nothing goes in between the floors. That's why you didn't see all the colors. So you can just kind of draw some important things. Look at what happens here. These are your longer lines. Longer lines represent higher energy, equals higher energy. Energy, see if I can spell here. Higher, whoo, goodness. Okay, look at here, visible, the lines are not as long. And then here's your infrared, not as high energy, so therefore, wow, that's really bad. So not as high energy because the energy difference isn't as high. But look at set difference. They're not going between the energy levels. They're going from one energy level to another energy level. But what's really important, look at the arrows. We see things when they come back down. When they come back down. Okay, why does this matter? So we're at the top of page 13. This is what I was just kind of talking about. That the electrons move in orbits at set energy levels. Kind of like, again, the elevator can't go between floors. So that energy difference between them are fixed. 1s, 2s. So remember when we're talking about those energy levels, the number in front gives me which energy level. They're a set distance. So therefore, the distance between this might be a 2s and a 1s, this is set. So it's consistently always going to give you the same amount of energy. Therefore, you're going to always get the same colors. This is the fingerprint for an element. I can identify an element. Since all the elements have the same number of electrons, you can identify an element. And we will show you some of these. My flash isn't working, so we'll actually show it to you in class tomorrow or when we see you again. Okay, so why does this matter? Well, because you know what they found out? This is the whole reason of this. As we're talking about this, I want you to keep in mind, electrons act like light. This is why we care. Because how we're talking about things travel is like light travels. So let's talk about light for a minute. There's wave properties of light. You can have interference, polarization. This is the reason you can have polarized light sunglasses which cut out some of the lights. Diffraction, refraction. Can you see light from a window, from a door around a corner of a hallway? You can, because light can bend. All of these properties are properties of a wave. Now what happened hundreds of years ago, maybe about 100 years ago, there were two divisions of scientists and they were really quite adamant. And one group said light is a wave, and they said this is my evidence that light is a wave because it has these properties. So they said, okay, we can calculate. So this is where the math comes in. These formulas are on your formula chart, so I would have that out, kind of looking at them and seeing where they are, and also your calculator. So look what this stands for. C is the speed of light. Okay, this is a constant. Okay, this is on your formula chart. This is why you get the formula chart on all of your tests. And it's 3 times 10 to the 8th meters per second. So this means, look at this units in meters and seconds. Okay, you have to have your wavelength in the same units to use this. F is called frequency, and again, this is how many times that wave is hurting you. Its unit is a hertz, or Hz, which is also a 1 per second. This is big or. Also, sometimes they put it like this. Because this means an inverse, that means it's to the -1. Okay, this is a lambda. Again, because we borrowed from the Greek, lambda is a wavelength, and that's how long that wavelength, either crest to crest. So it's like if you have a wavelength, that's one entire wavelength. That's how far from crest to crest. You can typically see them in meters, centimeters, or nanometers. Remember, nano is a nino. 1 times 10 to the -9th nanometers in a meter. But to use the speed of light, you have to have it in meters to use your formula. So to solve these, as we're going through it, this is a sample problem. We're going to use the guess method again. So remember, G was your given. What were you given? A wavelength. So G is your given. What are you trying to solve? In this one, you want to solve for frequency. Okay, E was my equation. Here's your wave equation. And what else do I know to help me solve that? Well, I do know the speed of light. This is on your formula chart. It's a constant. S substitute. Now, what I did, if you look at this, I go ahead and change for the formula. So I wanted frequency, so that means I'm dividing both sides by your wavelength. These cancel. This is how I get this. You don't have to do it first. You can do it after you get it. And then you plug it in. So this way, though, the math is already done, and all I have to do is calculate this in my answer. You solve it on the calculator, and there is my answer. Typically, you're going to get used to seeing these numbers. This is a frequency of something in the visible light wavelength. It's to the 10 to the 14th. I've told my class I look at exponents to know if that answer makes sense. I look at the exponents. So this is the wavelength equation. You know that everything travels at the speed of light. That's your constant. So if I give you frequency, you can find the wavelength. If I give you wavelength, you can find the frequency. So use this formula when you have wavelength or frequency. This is when you use this formula. Okay, so then there was another group of science that said, okay, no, you guys are wrong. Light acts like a particle because of these properties of reflection. And then there's this property called the photoelectric effect, and that's like how a remote control works, that if you shine a light with a high enough energy, that what happens, it actually kicks off an electron. That's the photoelectron. It's going to actually kick out little electrons. But again, this photoelectric effect depends on the frequency. Red light won't cause it, but some of your higher energy lights will cause it to happen. So what happened is Planck actually proposed that there's little packets of energy, and he called this a quantum. And what is a quantum? Is just that minimum quantity of energy that's lost or gained by an atom. Little packets of energy. Quantums. Then we also were calling these photons of energy, a little bundle. So he found the relationship. This is another formula. This formula is also on your formula chart. That's why you will be getting the formula chart on your test. So E stands for your energy. This is in joules. Okay, H down here is a constant, Planck's constant. Now I think on your formula chart it's 6.63 times 10 to the negative 34th. I will double check that. This is joules seconds. Remember, frequency uses, and I don't think we have to worry about this, frequency is in hertz, which remember is a 1 per second, so then your seconds cancel out, leaving you with joules. So this kind of formula will be, okay, so what's the energy of a wave? So look what it gave me. My given in this case is your frequency. I want energy. What formula has frequency and energy? Here's your equation from your formula chart. Energy equals Planck's constant times frequency. You know this constant on the formula chart. This is a constant, meaning it does not change, just like the speed of light. So then plug in, substitute your Planck's constant, substitute your frequency, just multiply. Look at what happens. Your seconds, because this is joules per second, times a 1 over second. Seconds cancel. This is why your energy is always in joules going through it. Why do we care about this? And it was actually Einstein that pulled it together. Einstein said, okay, groups quit fighting. You're both right. He proposed that there's a dual wave theory, and he's the one who called it then that photon, saying that there was a little that there was little packets of the EM radiation that was pure energy, carrying this photon of energy. So if it ever says calculate the energy of a photon, same formula, it's just being specifically talking about this little packet of energy. And again, this is how electrons behave. This is why we care. Electrons travel like the light. That's what you are calculating when we look at that. So look at your last one. What's the energy of a photon of red light that has a wavelength of 8.9 times 10 to the negative 7th meters? I want you to solve that. look at your formula chart. Look at your formula chart. Is there another formula? There could be more than one way to solve this. So I want to see how you go about solving this equation. I, meaning we, whoever your teacher is, wants to see how you solve this. And we will see you when we see you.